Okay, so 1.8 continuity, example 2, our objective is that the student will find where functions are discontinuous. Where are they not continuous? Now let's remember our definition of continuity, which is that continuity at a point A, we have to have the limit as x approaches a of f of x equal to f of a for a function to be continuous at a. And then of course if it can be continuous at every number in an interval, including the interval of all real numbers, if it's continuous at every number a, then it's continuous on the interval. Well, what about a here? Where is it discontinuous? Well, it's not even defined for x equals 2, so it's not going to be continuous there. There's going to be some sort of break in the graph of the function because it's not even defined at 2, right? 2 zeroes out the denominator. There is no point 2 something on the graph of f of x, so this function is discontinuous at 2. That's the answer for part A. F is discontinuous at 2. B. Well, you look at that and you're thinking, oh, that's a prime candidate for a value of discontinuity. And in fact it is, because f equals 0 is defined, f of 0 is defined, okay? When x is 0, f of x is 1. That one's defined. But the limit as x approaches 0 of f of x is the limit as x approaches 0 of 1 over x squared, which does not exist. So we have a discontinuity at 0. Okay, here you got a dne, does not exist. This one is defined, it does exist. Okay, of course the criterion we're using, of course, is that of continuity. Okay, we're looking at the three pieces here and seeing where, if anywhere, this is going to break down. At what point is it going to be the case that we can't say that the limit as x approaches a of f of x equals f of a? Well, what about C? For C, you've got, again, a piecewise defined function. F of 2 is 1, so that's defined. And, you know, we're thinking about, well, what about 2? What about x equals 2? Are we going to be able to write this equation for a equal to 2? Now, this expression, when x is not equal to 2, of course, we have a factorization here, which is x minus 2, x plus 1 is the factorization. And the x minus 2's can cancel, leaving you with x plus 1. And as x approaches 2, that would be 3. And so you have the limit as x approaches 2 of f of x defined, but does it equal f of a? No, it does not equal f of 2, and so we're going to have a discontinuity at x equals 2. Okay, so we needed this to be a good equation to have continuity at 2 for part C, but we don't have that. So the answer to C is f is not continuous, or it is discontinuous at 2. Now, here we've got, for part D, the greatest integer function. And that is a whole other ball game, because you get this crazy step function, and of course you have a discontinuity at every integer. Okay, the limit as x approaches any integer n of this greatest integer function, okay, any integer n, okay, -2, -1, 0, 1, 2, 3, you have a jump discontinuity. You jump up from one step to another. And so for the greatest integer function, the answer is that f is discontinuous at every integer value. Okay, so the graphs that we had, okay, part A, there was just a hole in the graph, so you've got a discontinuity because of that. Right, because this graph is going to be the same, except for one point, it's going to be the same as the graph of y equals x plus 1, because these x minus 2's can cancel because of the way the numerator factors. There's an infinite continuity in B. You can see there's an infinite discontinuity. The function blows up at 0. Now that is defined at 0, but it's defined to be 1, and so there's an infinite discontinuity at x equals 0. And in C, there is a discontinuity at x equals 2, because the limit, which is 3, the limit as x approaches 2 of f of x, which is 3, is not the same as f of 2, which is 1. So we're missing the equal part of the definition of continuity. We're missing the equal part, even though the other two parts were okay. And we see the countably infinite number of discontinuities for the greatest integer function in part D. In each case, the graph can't be drawn without lifting the pen from the paper, because a hole or break in the jump occurs in the graph. The kind of discontinuity illustrated in parts A and C is called removable, because we could remove the discontinuity just by defining f at the single number 2. Okay, and so if we just said let's just change this to 3, that would put this point right back on the graph, and we would have a continuous graph, because we'd be able to draw it without lifting our pencil from the paper. So removable is one of the 3 kinds of discontinuity. Another one is infinite discontinuity. You know, you can't draw that without lifting your pencil from the paper. So that's another kind. And then you've got your jump discontinuity, which happens for this step function, the greatest integer function, because you jump up from 0 to 1, 1 to 2, 2 to 3. You have a jump at any integer.